So far we had seen everything is with a resistive load, only the resistive load. We also have inductor together with a resistor as a load. So here you can see this is the SCR controlled rectifier. It's a half wave because we have only one. And here in the load side, I have the resistor and also inductor. So it's representing different type of load. So when we have this one, what is happening here? All the working principles are the same. So during the forward bias mode, I apply the gate voltage and I have the positive half cycle. This SCR start to conduct. When the SCR start to conduct, the current flows in the circuit. So at the same time, in parallel, because of the inductor property, the inductor start to store the electrical energy in terms of electromagnetic field. That is the property. So whenever you apply some kind of electricity or current through the inductor, it will go through this loop, right? This is so many loops are in the inductor. So when it goes, it start to energize this loop. So there will be some kind of magnetic field around this. It will store the energy in terms of magnetic field. That is the property or the nature of the inductor. If the capacitor means, the capacitor will also store the energy in terms of charges, electrical charges. That is the nature of the capacitor. Whenever the current flows, the capacitor will store the energy. Inductor will also store the energy. Okay, so inductor start to store the energy and then everything is okay. The first half cycle. The second half cycle, what's supposed to happen? The second half cycle, you are reversing the bias, right? So this SCR should not conduct anything, But because once the the polarity got reversed here in the negative half cycle, then this inductor already have some magnetic field, some energy inside. It will start to discharge this magnetic field through this opposite direction. So it means even though it's actually this one is little bit stronger than this negative or reverse bias of this SCR. So this magnetic field will still drive this SCR. So it will still drive this SCR. The SCR will conduct something. So instead of at this point SCR completely stop conducting, the SCR will still conduct little longer. So this is the alpha to pi. This is what we want the SCR to conduct at the output. But because of this inductor, the inductor will discharge the magnetic field. So even after in this negative half cycle, after the pi, this SCR will conduct for a short time. So that is why the output, this is the output voltage. So alpha to pi, we get the output. That is very good. But here in the negative half cycle also, the output, we are getting some negative output, right? This is the property of inductor. Whenever we have the inductive load in the application, we will have this effect. So this is called beta. So this point is called beta. So now you know two different points. This is alpha and this is beta. Alpha is the firing angle. That's very good. That's okay. We are controlling this alpha. This beta is really we are not controlling. This is depending upon the inductor. This is not really. That is why the output waveform in stuff like this, it's going like this, little more the negative side. So this is I'm not going to derive the formula for this circuit. This is the standard formula. You should remember 1 divided by 2 pi integral of alpha to beta. Alpha to beta, we are getting output. That is why we are putting the limit as alpha to beta, and the rest of them are the same. Vm sin omega t, d omega t, and then if you simplify this, integrate, and then you will get this formula. Vm divided by 2 pi cos alpha minus cos beta. And the average power is I square R, so that you can apply the value of the I square RMS. Once you know the V square RMS, and then you can calculate the I square RMS and then apply here, and then you will get the P. Okay, so here you should know the new parameter beta. So the formula have a new term cos beta. So, but we do not want to have this one, even though in the load or the application have the inductor, we do not want to have this effect. How can we avoid that? We are putting flywheeling diode in parallel with the load. For example, in my laptop, I'm charging. Maybe in my load, it has the inductor together with the resistor. So in that kind of situation, I get the output like this, but I do not want this. So I am putting this kind of flywheel diode in parallel with the load. So what will happen here? Everything is the same. So in the positive half cycle, it will conduct, that's okay. But once it starts the negative half cycle, it still conducts because of this magnetic field discharging. So this magnetic field, instead of going this way, going back here, we are putting this flywheel diode. So it means this, instead of going through this way, this will not take this path. This will go this path, and it will become more and more weaker. This magnetic field will die. So in this case, we will not have this beta anymore. So this is the output voltage. We supposed to get this somewhere here up to beta conduction. Because of this flywheel diode, the flywheel diode just bypass the magnetic field energy and avoid this negative conduction. That is the use of this flywheel diode. Okay, so I think the formula for this one is like this. Average voltage, output voltage, that is the VDC. And if you apply this formula, 0 to alpha, only it's conducting now. So everything else is the same. You know this R load, RL load. Then on the RL load, we have the problem of this magnetic field from the inductor. They discharge the current. Then we have the flying wheel diode. The complete power supply is like this. We have the transformer, and we have the rectifier, and we have the filter, voltage regulator, and load. So these diodes are, this is the one we focused on today. So we had seen so far half wave rectifier, and also we had seen the full wave rectifier operation. We know that full wave rectifier means we can use 2 diodes or 4 diodes. If you use the center taped transformer, then you can use 2 diodes. But if you want to avoid the center tape, then you can use the bridge circuit. And if you have the inductor, then you have the problem of magnetic field discharge. Then you have this flying wheel diode across. When the alpha is 0 degree, what is happening? When the alpha is 0 degree, then it acts like an uncontrolled rectifier because we get the full output. But when the alpha is 45 degree, what is happening? Alpha is 45 degree means it's conducting only from this 45 degree to 180 degree. Here we have the inductor, so that's why we have the negative side. And when alpha is equal to 90 degree, then what's happening? You can see here, as the firing angle is increased from 0 to 90 degree, the power supplied to the DC load decreases. It's becoming 0 almost. So here you can see here, and after some point, you can even, when you increase the firing angle to 135 degree, the circuit will act like an inverter. Inverter means it will invert from DC into AC. So you have to know the limitation of the firing angle. So up to what level you can increase the firing angle. So 0 to 180 degree. So you can increase up to 90, and then once you reach the 130 degree, 135 degree here, then it will becomes, the operation will change. Instead of rectifier, it will start to work like an inverter.